Today we're going to talk about the remainder theorem and the factor theorem. You will need to turn to page 13 in your packet to complete this. And by the way, if you're still struggling with how to do synthetic division, you need to go back and find the link and look at the information about synthetic division. The factor theorem states this: the value of the polynomial p of x at x equals a is the same as the remainder you get when you divide p of x by x minus a. In other words, let's pretend that p of x is a function defined as x cubed minus x squared minus 10x minus 8. And let's pretend that we took that polynomial and we divided it by x minus 3. If we do that, we would get x squared plus 2x minus 4 with the remainder of negative 20. And of course, this is how we write our remainder. We would have negative 20 over our divisor, which in this case is x minus 3. And it just so happens that if we were to find p of 3, in other words, if we took 3, put it into our polynomial function, p of x, we end up getting negative 20, the same thing as the remainder. So why do we care about this, you may ask? Well, sometimes you may just need to know what the remainder is for something. When you do the division, you may not need to know the whole rest of the division problem, and if all you need to know is the remainder, you can skip that long division process and just take your value and put it into your function, and that gives you the same thing as your remainder. But honestly, the remainder theorem is really not that important to be able to find the remainder, for at least what we're going to be doing in most cases. It really is important when we think about applying the remainder theorem to help us find factors. And that leads us to the factor theorem. Let's think about what it means for something to be a factor. A factor is anything that we multiply to get something else. If something is a factor, then it goes into another thing evenly. For example, 18 divided by 6 is 3. There's no remainder. 6 goes into 18 evenly, and that's because 6 is a factor of 18. We can multiply 6 by another whole number and get 18. Because of that, the factor theorem says if p of a equals 0, then x minus a is a factor of p of x. Using our original function, p of x equals x cubed minus x squared minus 10x minus 8, and let's take that function and let's divide it by x minus 4. If we do that division, we get x squared plus 3x plus 2, and there's no remainder. In other words, the remainder would be 0. Now let's keep in mind what the remainder theorem told us, and said if we took the value from our divisor, put it into the function value would equal to the remainder. So if I take 4, put it into my polynomial p of x, so I do p of 4, I end up getting 0, which would be the remainder, which means x minus 4 goes in evenly. Let's look at some of the sample problems now on page 13. Let's look at problems D, E, and F specifically. These three problems use the words zero, solution, and factor. What you need to keep in mind is that all three of those things mean the same thing. If something is a zero, it is a solution, and it is also a factor of the polynomial. All three of these problems will be done the same way. Let's focus on D, determining whether x equals 2 is a zero of p of x equals 3x to the 7th power minus x to the 4th plus 2x to the 3rd minus 5x squared minus 4. Now there's two ways to do this. The first way is we could simply find p of 2. We start by substituting in 2 for all of our x's. So we get 3 times 128 minus 16 plus 2 times 8 minus 5 times 4 minus 4, which equals 360. So obviously p of 2 is not a 0, because if it was a 0, then p of 2 would be equal to 0. Let's see what happens if we use synthetic division to solve this problem. I've rewritten p of x to show all of the 0 values. In other words, those x terms that don't have any coefficient other than 0. So p of x is now 3x to the 7th plus 0x to the 6th plus 0x to the 5th minus x to the 4th plus 2x to the 3rd minus 5x squared plus 0x minus 4. And of course we need all those zeros for our synthetic division. So now we do our synthetic division, and you can see we get down here to the end, and 360 is our final answer, which we know is our remainder from our synthetic division. So again, we realize that 2 is not a 0 of p of x. Let's now look at problem G. Use synthetic division and the given factor to find all the zeros of the function y equals x cubed plus 3x squared minus 5x minus 4, and the given factor is x plus 4. What this boils down to is we are going to factor the polynomial x cubed plus 3x squared minus 5x minus 4, and we already know that one of the factors is x plus 4. I've set up our synthetic division, and notice that I have used negative 4 on the outside instead of plus 4, even though it says that we are dividing by x plus 4. Keep in mind what the remainder theorem said. It used the terminology x minus a. And this is another one of those places where we always take the opposite sign. Anytime there's the minus in our original theorem, always remember, change the sign. If we do this synthetic division correctly, it should be equal to 0 because of the fact we're told that x plus 4 is a factor. When we complete the synthetic division, we get 0 at the end, which means we had a remainder of 0, which means that x plus 4 was indeed a factor. These remaining coefficients are now our focus. Let's keep in mind what happens when we do synthetic division. These numbers now represent the coefficients of something that is called our reduced polynomial. In other words, the answer to our division problem is x squared minus x minus 1, because we started off with a degree of 3 up here, and now once we do our synthetic division, we take that down by 1, and our new answer is x squared minus x minus 1 based on the coefficients from that last line of our synthetic division. We're not finished yet because we are told to find all the zeros of the function. We've only found one, and that being negative 4. In order to find the other zeros, we have to factor the remaining polynomial. Now I'll go ahead and tell you, if we can use our Xbox method or whatever other method you want to use, you're not going to be able to factor x squared minus x minus 1, which leaves us with one other possibility. We need to now take this quadratic polynomial and use our quadratic formula to find the remaining zeros. When we take the coefficients from our quadratic, a is equal to 1, b is equal to -1, c is equal to -1, and we put it into our quadratic formula, we get this expression. And when we simplify that expression, we get it all the way down to 1 plus or minus the square root of 5 over 2. And those are the other two zeros. 1 plus square root of 5 over 2 and 1 minus square root of 5 over 2. For the final sample problem, let's do problem H. Problem H says, find the values for k so that each remainder is 5. We have the polynomial 2x squared minus 8x plus k divided by x minus 7. Now that k can be any number. Our goal is to find that number. And once we find that number, if we do our synthetic division using 7, then 5 should be our final answer. Let's approach it from that point to start with. Let's do our synthetic division even though we don't know what k is yet. After doing our synthetic division, we get to the end and notice we have 42 plus k, because in our final column we have k right here and 42 right here, and we have to add those, and that's how we get 42 plus k. This 42 plus k is the remainder when we do that division. Remember, that's what synthetic division is all about. So 42 plus k must equal to 5 according to the instructions given to us in the problem. So to find k, we simply say 42 plus k equals 5 and then solve for k. And when we solve this, we know that k equals negative 37. So to sum this problem up, we do our synthetic division, even with k in our problem, get our final answer, and set that equal to the designated remainder and solve for k. If you go back to Canvas, you will find every sample problem and all of the work for all the problems on page 13, in addition to all of the answers to the homework on page 14. Please use this video as much as you need and look at the sample problems on page 13 in addition to the ones done here on the video to help you understand what is going on. Good luck.